Okay, what can we do? So if we're trying to, what is it that we're trying to minimize or maximize here? Fencing. Okay, so we're trying to minimize fencing, right? So then, now you got to kind of think of this in terms of, and this is what I want you to really get good at. I want you to think about this in terms of what a graph might look like then, right? So what could we call that? Kind of a perimeter-ish thing, I guess, call it P for perimeter. So we want to be able to do something where we're going to graph P as a function, perimeter as a function of some variable, right? Because we want to minimize fencing. If we could do that on graphing technology, then we could look for a minimum, right? Minimum value for that function, okay? Well, what is the function here? If we want to write a function down for perimeter, and here's our picture we can use, right? We've got this fence. It borders a river on one side, I guess. Is that right? So we've got this pasture. We want to create this rectangular corral, or what are they going to call it? I don't know, but someplace to put the animals. What's going to be the formula for that modified perimeter? X plus 2y. Okay, that's the function that we want to minimize. What's going to be hard about that, though? If I want to try to graph that, there's my P. Well, it doesn't have to be quadratic, but there's something that's going to make this really difficult to graph. It's got three variables. Yeah. It's got my output variable, but it's got two input variables. It's got two independent variables, right? We can't really deal with that, right? A lot of what we do in calculus, this is taken from our calculus book, by the way. So this is a problem that you guys will do in a couple of years just without graphing technology. So a lot of what we do in calculus is we've got to come up with some way to write that. We call this a primary equation because it's the equation for the thing that we're trying to minimize or maximize, trying to minimize perimeter. We need to be able to write that as a function of one variable. Okay, so logically, if there were no other information given, if there were no constraints, I could make it 0. It'd be a pretty stupid question, right? I'll just make the pasture have no size at all, and then have an area of 0 or something, and then the perimeter is 0. Problem solved. But that's not a very useful pasture, right? So there's going to be some information given to us that's going to be what we might call a secondary equation. I like to call it an equation of constraint because there's going to be some constraint placed on this system so that it's not a stupid question, right? What's the constraint here? What's the other piece of information that kind of gives us some limitations? Okay, so the area. Yeah, the area must contain 245,000 square meters. Okay, so that gives us another piece of information to work with, right? That's a second equation. It constrains the problem a little bit, right? So what's the advantage of that? Well, first of all, how would I use that in an equation? Okay. How is that useful? Well, I could graph that, but I'm not really interested in graphing that because that's not the question that's being asked. They want us to minimize perimeter, but that still is very useful to me. Let's just focus on the equations for a second. How come? Notice that the equation of constraint, or the secondary equation, relates the x and the y. Well, those are my two independent variables, right? So what does that allow me to do? Substitute, right? You see the strategy there? That's why I need that secondary equation. I need some other equation that relates the independent variables so that I can solve for one in terms of the other, right? And in this case, it doesn't really matter. Sometimes it really does make a big difference. Sometimes, depending on how complicated this equation is, and we'll talk about this more in a couple of years, but sometimes it really does make a difference. It's much, much easier to solve for one and substitute than the other, and that'll be clear when you get there. But for now, let's just solve for y, how about? So if I put in y equals, if I divide both sides by x, 245,000 divided by x, I'll put a box around it because that's my substitution equation. And then I'll just substitute that in up there, right? So what's that give me then? If I plug that in, I now get P equals X plus 2 times that, right? Right? And I could simplify that and come up with, finally, I could get P, and I'm going to call this now, I'm going to call it P of X, right? Because now I've got perimeter as a function of X, which in our problem is the width of the pasture, right? Whatever you want to call it, the length or the width, whatever you want to call that dimension. What am I going to get? 490 if I just multiply the 2. There's my function, right? Now I can graph that, right? Everybody get that? Okay, I can graph that, but here's the other part of this I want you guys to kind of think about a little bit. I can graph that. Where is this function defined? X can't be 0 because I can't divide by 0. But anything else is okay mathematically, isn't it? Right? But this isn't just a math problem, right? This is a math problem that represents a situation that's a geometric, real-world situation. So in terms of that problem, X really couldn't be negative. Wouldn't make any sense. It has to be bigger than 0. Is there some upper limit to how big it could be? Say it again. Yeah, I can see where you might think that, because there's a number that seems like it's an upper limit. But and this is getting kind of complicated. I mean, this is a little tougher one than the one I gave you guys. But think about this now. If this is going to be an area, if I make X really small, then Y is getting really big, isn't it? Right? Conversely, if I make X really big, Y is getting really small. Right? Well, if there's going to be a finite amount of area enclosed in this, and Y is getting really small and X is getting really big, if Y were to go all the way to 0, how much area would be in that? 0, right? So it can never quite go all the way to 0, but as it gets closer and closer to 0, do you see that X is going to have to get bigger and bigger without bound? And so really, there is no upper limit to this. It's not very practical, probably, to have a pasture that's 1 centimeter wide and, 1,000,000 miles long. That's not going to be probably a very good choice for a pasture. But if I could do it, right? That's going to use a lot of fencing, right? So my domain in this case would actually be something like that, right? There's no limit to how long that fence could be, right? As long as as Y got really small. But I'm just going to graph this thing on that domain and just see what I get, right? Let's do it. Let's see what we get. If I go into Desmos, let's see. Okay, well, I don't see much there, do I? If I zoom out, presumably, I might start to see something at some point, hopefully. So there it is, right? Okay, well, I don't want the negative one, do I? I want the positive one. But what do you notice about this? It's weird. Yeah, it is kind of weird. But it clearly does have a minimum, doesn't it? Right? My minimum is right there. So what is going to be the value of X? 700. So based on that picture, the length of the pasture parallel to the river should be 700. What's the amount of fencing I'm going to need to make this pasture then? 1,400, right? Because aren't I graphing P of X, right? I'm graphing my perimeter function as a function of X. You see that? And so now I've got, look at that, that's pretty cool. Now it gave me the point gave me the minimum. And so if I want to know what the dimensions are, okay, the length is going to be 700. I can just go back to where to find out what the width should be. Yeah, where the y equals. I put a box around it, right? My substitution equation. If I just plug 700 in there and evaluate that, I'm going to find out what y is. I think it's going to be a 350, isn't it? We found that the perimeter was 14, right? See how that works? So maybe that gives you a little insight into how that one worked in 5.2. And that's why I gave it to you, because this is what's coming down the pipe for you in a little bit. All right, so new stuff for today. I want to look at, this is pretty cool. So let's say we've got some polynomial. Okay. First thing I want to do is take that polynomial and let's see if we can write this in a little different form. I'm going to write it in what's called nested form, which is it's just bizarre. We don't do this very often, but it's going to prove a point for today. It's going to give us some insight into how we can take a really good shortcut to evaluate polynomials. What if I were to, the biggest power of x is x cubed, right? So what if we did something like this? I'm going to start the ball rolling, and you guys see if you can kind of finish this up for me. So I'm going to start off by saying the first thing I'm going to do here is I'm going to take x and I'm going to multiply by 4, and then I'm going to add 3 to that, okay? And then I'm going to multiply that by x. Okay, what have I just done there? I've taken 4x plus 3 and I multiplied by x, which is going to give me 4x squared plus 3x. Okay. If I want to keep building and building towards this polynomial, you see that I've really just started to kind of account for that term and that term, right? And each time I'm going to add something to this and then multiply by x again. So what's going to be maybe the next thing I add to this, do you suppose? At this point, what I've got, I'll keep kind of a running tally of what I've got here. At this point, I've got 4x squared plus 3x. So would you agree that if I added 2 to this and then multiplied by x, I'm getting a little bit closer to what you see what I'm saying? Right? So if I add 2 and then I multiply the whole thing by x, that helps because that gives me now 4x cubed, 3x squared plus 2x, right? And then all I've got to do now is just add 1 to that, right? Get the idea? Okay. So what if I were trying to evaluate this polynomial, let's say like at -2? I could use this nested approach, couldn't I? Right? I could take the -2 and I could multiply by 4, right? Add 3, multiply that by -2, add 2. I forgot the last part. Plus 1. So there's the whole thing. Add 2, multiply by x, or by -2 is x, right? That's what we're plugging in. And then add 1. Do you agree? That's a different approach. That's different than just straight evaluation. If I just plug it into the polynomial in standard form, I'm just going to take 4 times -2 cubed plus 3 times -2 squared, etc., and just get an answer. And that's fine to do, right? What's the advantage of doing it this way, if any?
That's easier.
Well, in a way it's easier because you deal with much smaller numbers. Okay? Right, so I could take the polynomial in nested form and just kind of work my way out. Okay, here's kind of a shortcut way of looking at that. So I'm going to rewrite this thing here. So we've got p of x, once again, is 4x cubed plus 3x squared plus 2x plus 1. And let's find p of negative 2. Okay, we can use what's called synthetic substitution and take advantage of that process of just nesting the polynomial. So here's a couple ways you can write this bracket. Our textbook does it a little differently, but usually it's written like this. You write it as a big L, and then all you're going to do is you're going to put the coefficients up here of the polynomial. So this is going to be a 4, 3, 2, and 1. And you can't skip any rows. If there's a missing, one thing I'll tell you right up front, if there's a missing term, like if there's a missing power of x, you have to put a 0 coefficient in there. But that's going to be pretty common for us when we're doing the stuff we're doing in this section. And then down here at the end, oops, down here at the end you put a box. And then out front, you're going to put the value of x that you're plugging into the function, you know, where you're evaluating it. So I put like a negative 2 in this case. Okay. To do this nested evaluation process, it's really simple with this synthetic bracket. All you do is the first number, you just drop straight down. It goes there. Every time a number pops down below the bracket, you multiply by the constant out front. So negative 2 times 4 is, and you add. And you just add vertically. 3 plus negative 8 is, okay? A number popped down there, so what do? I multiply by this number. Notice you just shove it up there. The result you just push up there diagonally, right? So negative 2 times negative 5 is 2 plus 10 is, and 1 plus negative 24 is negative 23. Well, what do you suppose p of negative 2 is? Negative 23. That's pretty cool, isn't it? Right? Okay. Try that. Grab a Chromebook real quick. Just want you to try this one. Wait, how? You cut the 5 through the 4 pounds? No.
By the way, I already have a scholarship there. If I read another group, you could do like scholarship.
So iOS.
Yeah, okay.
Okay, so here's what I'd like you to do. Oh, real quick, just so you know, in our book, in our online textbook, in the notes, if they're not up there yet, I'll put them up there like right after class for 6.5. This is the way it's a little different. That's the way they write their synthetic bracket. It's kind of, it's a little strange. They put a little bracket out here where you put the value you're pushing into the function, and then they line up the coefficients with a line down here. You just do kind of the same thing though, right? So that's where the answer would end up being. Okay, but it's the same thing when you look at that. All right, try something. Go to the 6.5 assignment, and just try one of the first 3 problems.
Don't you think Chromebooks actually work?
Are they not working?
No, they never really do. I think it's for every.
Okay, so this might seem like a real big swing here, but I'm going to look at division. Okay, so why don't you close those up for a sec here. Take a look at this. So let's kind of remind ourselves how division works. And we're going to look at polynomial division, but just a good model for that is just regular long division. So let's just look at real quick, let's just kind of go back and look at a long division problem using numbers. So I would write this. I'm going to do long division. We just write it like that with that. Okay, remind me, what do we do here? Okay, good. So we've got the number 12. Does it go into 2? No, it doesn't. So we got to move over and say, does it go into 27?
Yes.
It does. Goes in twice. And then what do I do with that 2? Okay, I'm going to multiply the 2, right, by the 12 and get 24. And I'm going to subtract, right? 27 minus 24 is, now what? Drop the 7. Same thing. 12 goes into 37. 3 times with, okay, and then, now what? I can't just add zeros to this because that'd make that number a lot bigger.
No, it's a decimal.
But what's my answer? Okay, that's my remainder, isn't it? Right? Think what that's saying then. We're saying that 12 goes into 277 23 times with 1 left over, right? But the 1 left over is what 12 is trying to divide into, right? So if I wrote this answer out, it would just equal 23 plus 1/12. As a mixed number, we just write that as 23 and 1/12. But a mixed number really means this, doesn't it? Right? Everybody agree? Okay. All right. So another way of saying that would be 277. You tell me this. Here's another way we could do this. 277 equals what? 12 times 23 plus 1, right? Everybody agree? Okay. All right, so let's try the same thing with polynomials. Okay, and it's the same process, it really is. It's maybe a tiny bit harder, but not a ton. You just have to be organized, that's the key. So when we write this down, which number goes where? Which number goes out front? Or which polynomial goes out front? The denominator. Okay, so this one goes out front. And it doesn't really matter if this one were missing a power of x. It doesn't matter. You don't have to like hold the place with that one out there. It's not a big deal, and you'll see why. But the polynomial that's in the numerator that goes inside the bracket, and this bracket's got a name, and I can't remember what it is, but you know what I'm talking about, the long division bracket. What do you notice about the polynomial that's in there? Is it missing? Okay, it's missing the quadratic term, isn't it? It's missing the x squared term. So we do have to hold that place in here, and this will also become really clear why as we go through the process. So it'd be 6x to the 4th plus 5x cubed plus 0x squared plus 2x plus 8. Okay, what do you think we're going to do? I mean, it's exactly analogous to what we did last time. Okay, so we want to see, we're going to look at how many times does this polynomial go into parts of this polynomial. And all you really have to focus on is the leading term here and the leading terms here, right? So x squared does go into 6x to the 4th. How many times? So really the question I'm asking here then is this big long, 6x to the 4th divided by x squared is what? 6x squared. See what I'm saying? So x squared times what is 6x to the 4th? 6x squared. What do you think I do with that 6x squared? What did we do here? When I got a 2 up there, what did we do? We multiplied by 12 and found the difference, right? So same thing here, right? 6x squared, I'm gonna distribute, I'm gonna multiply it times the denominator. Just distribute it all the way through. So 6x squared times x squared is 6x squared times 2x is 12x cubed, okay? And 6x squared times negative 5. Okay, and we're just gonna subtract that away, right? So I'm gonna put a negative sign out there, and we'll subtract it, and then what do we get? Well, of course, the first terms cancel. That's why we picked the 6x squared, right? So these guys cancel. What about here? What's 5x cubed minus 12x cubed? Negative 7. Oops. 0 minus negative 30x squared. And then I'll just bring these straight down because I'm just subtracting 0 from those, right? Okay, what did we accomplish? That was a step in the right direction. Okay, we reduced the order of the polynomial, the degree of the polynomial by 1. And now we just start over. Okay, so now what do you think? How many times does x squared go into negative 7x cubed? And the answer is no. What is that? Negative 7x, right? Okay. Right? In other words, you could kind of just say to yourself, this is how I do it. I would just say, okay, x squared times what is negative 7x cubed? Well, negative 7x, right? So that's the next term in the answer, right, in the quotient. So now we're going to distribute that through, right? So negative 7x times x squared negative 7x times 2x, negative 14x squared, right? Negative 7x times negative 5. Okay, and I'm going to subtract that whole thing away. So of course, first terms cancel. That's the whole point. Then what? 30 minus negative 14 is, so we're going to get a 44x squared, 2 minus 35, right, negative 33x, and then I got my plus 8. Okay, now what? Same thing. How many times does this x squared go into 44x cubed, 44x squared? 44. So I'll distribute the 44 all the way through. 44 times 2x, 88x. 44 times negative 5 is what, negative 220? And I'm going to subtract the whole thing. And what do I get? Well, the x squared terms cancel. Negative 33 minus 88. 8 minus negative 220. Okay. And now what? Okay, but what happens? That's got to be the remainder, doesn't it? Because now x squared no longer divides evenly into this. This is a smaller degree polynomial down here than the denominator, right? Make sense? So that becomes our remainder. So then our answer would just be, if we want to write this thing out, it's just going to be this polynomial, 6x squared minus 7x plus 44 plus the remainder of negative 121x plus 228, all divided by the denominator, right? That's what remains over the denominator. Okay, everybody see that? Okay. So real quick, last thing, I guess we're out of time here. How else could I write this answer? Oh darn it, that whole thing was equal to this, right? So how could I write that? What if I multiplied each side through by the denominator? Do you see that I just get this? 6x to the 4th plus 5x cubed plus 2x plus 8 equals, if I distribute that through, I'm just going to get the product of this polynomial times this polynomial, right? Plus that remainder, because those would cancel, right? Everybody see that? All right. So that's the last section on the assignment. So do those. That's a total of 7 problems for tonight. That's it. First section and then the last section.
So, do you have a work day tomorrow?
Probably partially, yeah. I got one more thing to show you that won't take very long on this, and then I could probably see my way to give you one.
So one thing I've always had trouble with is multiplying double-digit numbers by 11.